Good morning, everyone. First of all, apologies for the delay. Today, we're going to have Jorge Sanchez-Almeida talking about faint double peak H-alpha emission, discovering the halo of low redshift galaxies. It is produced by rocky intermediate mass black holes. Since we are having a lot of delay, I'll just pass the word to Jorge. I just remind the PhD students that they should report their attendance via the chat of the Zoom session. Thank you. Jorge, all yours. Bye-bye.
Okay, so let's pretend that nothing happened, and I will start with actually the work that we have been doing during the last year or so. I'm very excited about what I'm going to tell, not just because of the beginning. So what I will describe is something that is in a paper. It's now in press in IMBH, and it's about the discovery of a faint H-alpha emission around galaxies with double peak, which we think they may tracing intermediate mass black holes. Okay? So this is a work that has been carried out in collaboration with the whole Daigo's team at the NC. Joao Callao, he's not here, he's at home, and he's responsible for most of the research that I will experience today on. Then Annalisa, she's here, is in charge of the follow-up on the HST of the targets that I will introduce, and then Casiana and Jose Miguel that we will know. So the talk has been prepared to follow these guidelines. First, I will talk about what we were after and what actually we found. Then I will explain what we did, particularly the use of something that is called MUSE-Wide, fields of full database of MUSE-Wide. Then I will talk about the properties of the H-alpha emitting clumps, and then I will. This is a description of what are the properties of what we have found. Then I will try to explain in physical terms what we have found. Keeping in mind all the observational constraints that we have, what could be the physical origin of this emission. And this is where intermediate mass black holes come into play. And finally, I will try to explain in a couple of slides that we do expect play with intermediate mass black holes, despite the fact that we haven't found a lot, just few. Sorry?
Can you near
the mics?
Yes.
So like here, I will do my best. So I was trying to say, but I need to see the screen. So we in our team, we have been looking for something some of you might be aware of, others don't, but we have been trying to find the gas that is predicted to be feeding star formation in galaxies. This is cosmological gas that has been in the intergalactic medium forever, basically from the origin of the universe, and is kind of falling into the gravitational wells containing galaxies, and it is gas info that maintains star formation rate in galaxies. Okay, so this is something that was very clearly predicted from numerical simulation, but it has been extremely hard to observe. And so there are a lot of indirect hints that we don't have kind of conclusive proof yet. But I mean, the closest thing, from my point of view, that we have for the existence of this gas is an observation from MUSE-Wide by exhaustive et al. That was published a few years ago, which basically tells that if you go deep enough, the whole universe is emitting in line alpha. Really, any line of sight that you can think of, if you have the sensitivity to see the photons, they are that region is produced line alpha. Okay, the idea that we have, and we had this idea, we have been trying to go after this idea for quite some time, is to try to find this emission, but rather than in Lyman alpha, in H-alpha, which is expected. I mean, all the physical processes that produce Lyman alpha will also produce H-alpha. So we wanted to find the H-alpha emission of this gas around galaxies that is feeding the star formation. Now, what we found is that yes, there are some clumps of H-alpha, but they don't seem to be tracing the gas they seem to be tracing intermediate mass black holes. So those are seeds that are, for some reason, needed, which I will come to this thing later on. But they have been extremely hard to observe. So that the seeds from which supermassive black holes feed, but this process of black hole merging is not very efficient. So you expect to have lots of leftover in the present universe of this process, and so intermediate mass black holes around galaxies. What we did, as I told you, we have in this business of trying to find weak H-alpha emission around galaxies. And the first thing that we tried, and this goes back to the thesis of Amanda Olmo Garcia, was to try to get very deep narrowband images in H-alpha around galaxies that we expected to have H-alpha in emission, this gas around them. For some reason, we thought that they were accreting gas now, and we looked for that thing. But this is not. This was proven not to be a very efficient process. So, and the reason is something trivial that you might have heard many times, but I'm going to take a couple of seconds to explain in some detail what happened. So this is just a mock spectrum, the blue line here, with an emission line. And it's an emission line on top of a background with lots of noise. Now, if you use a narrowband filter to select the band path and to detect the signals, together with the signal, you are adding all these nodes. And this noise is really a killer. So if you somehow manage to select just the band path of the emission line, then you gain signal to noise by a large factor. In this simulation, this is different realizations of the noise. And you see that the red dots, which is what is in this band path, has a scattering which is much smaller than the scattering you get from a one. And so it's obvious that you have to go, if you want to go deep in emission lines, you have to go to spectrograph. And but the issue is that in order to find this gas around galaxies, you also need a large field of view. And so you need a spectrograph plus a large field of view is an eye field. And if the field of view has to be large enough, then there's only one instrument, which is MUSE, capable of really putting together these two constraints. For those of you that don't know, MUSE is in one of the VLT telescopes in Chile. In a single exposure, it covers the whole, almost the whole spectral range not almost, the whole spectral range from 4,500 Armstrong to almost 900, 500 Armstrong. The spectral resolution is about 3,000, so it's fair. The field of view is not around 1 per minute square, and with a sampling of 0.2 arcsecond. So for every point in this in this 1 arcsecond square field of view, you get the spectrum simultaneously of the whole spectrum, of the whole spectrum range, of the whole visible range. Now, in addition, I mean, 1 minute is really not a very large field of view. So we need things that are bigger, as I will probably say more later on. And fortunately, there is this public data set taken with MUSE that is called MUSE-Wide. And it's really fields around the good south exposure. So are all these fields around good south. All together, they cover a field of view of over 44 arcminutes, which is sufficient, so to say, for what we were trying to do. So we're trying to, with this data set, which has this the right depth, the right field of view, and the spectral coverage that we need, we wanted to see whether there are emission in H-alpha around galaxies. Since we want to detect H-alpha, we select in this field of view all the galaxies with a redshift that is low enough for H-alpha to show within the bandpass of MUSE. Okay? And this corresponds to 0.42. The redshift corresponds to 0.42. And altogether, in this field, there are 164 galaxies. Now, what we did was for every one of these galaxies to construct an narrowband H-alpha signal around the emission corresponding to the redshift of the central galaxy. So for every galaxy, we have an H-alpha image, which is constructed from with all the emission in a bandpass tuned to the redshift of the galaxy. And after a long work but I have to see really no time to spare in detail. We identify in H-alpha images clumps that are emitting but don't show up in continuum. Okay, altogether, we detected of the order of these 120 emitting clumps. Okay, so for every one of these galaxies, we constructed the H-alpha images and looked for visually for this is something Joel did for emission in H-alpha which is not in continuum. Okay, and we selected those points. And those points are these 118 points. Now, this is again the same rendering of the previous image. So there's something that's emitting in H-alpha, but not in continuum. And for you to have an idea of the scales that we are sampling, we are going all the way out to the effective, sorry, to the via radius of the apartment. So remember that the via radius of a galaxy is often huge compared with the optical radius, typically 50 times the effective radius. Okay? So this is the clump, this is this clump, and this is the central galaxy. Okay? Now, properties of these 180 clumps. So first, the flux densities are low, of the order 10 to the minus 17.5 or so in CDS units. The surface brightnesses are very low as well. The luminosities are very large, but remember that these galaxies, even though they are local, since they are no redshift 1 or 2, but they're still a significant redshift, so the luminosities are very large, despite the fact that the fluxes are also very low. If you make the game of trying to estimate the mass of emitting gas, counting the number of so H-alpha photons that you get, you can estimate the mass of gas that is emitted and happen to be in every clump of the order of the 5 to the 6 solar masses. So this is gas of emitting gas, and they are the clumps are typically unresolved, so of the order of the resolution of MUSE. Now, two additional properties are particularly important. I'm going to say, and in a sense, tell that these clumps know the existence of central galaxies, even if they are very far from the central galaxy. Now, the first one is the distributions of atoms. So if you have the central galaxy and you have the clump here, and you make a histogram of the number of times that a clump appears with a given azimuth with respect to the major axis of the galaxy. So this is the angle that is represented here. The clumps happen to be aligned with the major axis of the galaxy. So they avoid the directly expected to the main plane of the galaxy. And if you make a histogram of the distances to the center of the, the distance of the clumps from the central galaxy, they show this distribution in blue, and sort of peaks at the effective radius of the galaxy. So remember that this is 50, 60 times the effective radius of the galaxy, very, very far from the galaxy, but knows of the existence of an effective radius. We also tried to find whether these things were emitting radio and X-ray, and they don't, or at least not with the upper limits that the current surface, deep surface in X-rays and radio within have. We do, however, detect a few of them in the HST images of the field. As I said at the beginning, analysis of this now. This is a kind of long introduction to tell what is the big surprise of the world. And the big surprise is that the line that we detect very often have two peaks. Two peaks where the drop in between the two peaks is at the redshift of the central galaxy. So this is emission in something which we think is H-alpha with two peaks with a drop at the redshift of the central galaxy. That's what we found. In addition, I mean, this is stacking of all these 180 different targets. The signal to noise ratio is significant to clearly see the double peak here. And it's important to note that first, we don't detect H-beta, and we don't detect the typical oxygen lines of H2. Okay. Again, this is the same thing as before. this is stacking, with a zooming in wavelengths so that the separation is clear. And also to point out that despite the fact not all the peaks that we detect are double peaks, even if you average only single peaks, they tend to avoid the central double. It's like the single peak seems to be like a double peak without one of the peaks. Okay? So we get plenty of double peaks, so 40% of the time the line is double peak, and even if it is single peak, the single peaks are distributed, try to avoid the central wavelength. The peak-to-peak separation is of the order of 175 kilometers. Okay, so these are the constraints, and I'm going to try to explain what could be causing this double H-alpha emission. And this is a kind of table, it's a summary of the things that we explore in the paper. And these are the observations that we try to fit. So the surface brightness that is observed, the number densities of how many of these points you get per galaxy, whether you are able, the mechanism is able to produce a double peak or not, whether the drop in the separation of the two peaks coincides with the redshift of the central galaxy, whether you are able to account for the ratio between H beta and H alpha, whether you don't get continuum, whether they are kind of unresolved, and whether they satisfy the spatial resolution, whether they are simultaneously aligned with the major axis of the central galaxy. Now, remember that we started the whole business trying to find cosmological gas that fit in this formation, but this is not the explanation. I could argue in various ways, but one of the obvious things is that this is a cosmological gas, so you expect it to be very limited, so very limited gas. So it's very hard for you not to produce H beta together with H alpha. For instance, thus obscuration cannot account for that. At the same time, the cosmological gas, it's very hard to produce double peaks. I mean, it can produce double peaks if somehow the gas that has been accreted shocks with the gas that is in the circumgalactic medium. And then you have a shock, you have two velocities, and so you might produce speed on the line. But one of the peaks is going to coincide with the redshift of the central galaxy. I'll say it again because I think this is an important point. So even if somehow you manage to, so suppose you have gas accretion and you have gas in the circumgalactic medium. So you have gas from the intergalactic medium falling into the potential of the galaxy, it shocks with the gas that was in the circumgalactic medium. So you have two velocities. You have the velocity of the gas falling in and the velocity of the gas that wasn't falling in. Typical velocity of the gas in the halo is the same velocity of the central galaxy. So one of the peaks is going to be at the velocity of the central galaxy. But this is not what it's also. So it's probably not cosmological gas. I mentioned shocks, and again, it's the same angle. So the shock can be produced by this gas in the form from the intergalactic medium, or even the galaxy winds that are like interacting. It's winds produced by the galaxy interacting with the gas in the circumgalactic medium. You have two velocity components, but one of them is going to be at rest with the central galaxy, the other is in the circumgalactic medium. So we can cross out also shocks, interlopers. So one of the I didn't mention this thing, but one of the problems of having broadband images to try to detect the emission line is the fact that if the bandpass of the filter is broad enough, it has a high capability of picking up sources that are in the background, line alpha meters, H2 meters, and so on, because well, the bandpass is the problem. The problem is much less severe in this case because the bandpass is very, very loud. So, but in principle, we might have some potential. So, line alpha emitters in the background that lead into the bandpass that we are there. Okay, but I think we can discuss this combination in various ways. One of them, simple one, is very hard to figure if you have a backend combination. It will be distributed, knowing the presence of the central galaxy, trying to satisfy this constraint on the azimuthal distribution. That tells that whatever is emitting there knows of the presence of the central galaxy. And another thing is simply when you take the typical velocity functions of the contaminants, 5.5 meters, and you know your bandpass, you know how hot they are, you know the redshift that they should have. So you can estimate the number of counts, failed counts, that you can have through your field. And it's happened to be well below 10%. So even though we cannot completely discard the contamination of 100% of all the sources, so most of them are not going to be interlopers, are not going to be contaminants in the market. So we cross out interlopers, and then we discuss a little bit about galaxy outflow. So there with the gas inflow, galaxies are going to be outflows, either driven by AGNs or driven by star formation. And again, can this thing explain what you observe? And again, they can be discovered because producing these 2 peaks is very hard with the drop at the redshift of the central galaxy. So we cross out and what? And let's now think about expanding bubbles. So suppose that you have a little expanding bubble somewhere in the heel of the gas. If that thing explains if you integrate the presence of a bubble peak in there, in principle, if you have, this is a very simple schematic, if you have an expanding bubble, you're here the observer, you integrate the light that comes from this bubble. So in this situation, what you get is a top hat emission line. But if you have dust in the expanding shell, then you can create a central drop. Now, the question is, yes, you can produce two, with this expanding bubbles, you can produce 2 peaks centered in the right wavelength, so the central wavelength, the bubbles are somewhere in the intergalactic medium. But the problem is that the distribution is not the one. So you expect to have this bubble right where you have star formation, so in the center of the gravitational position. We see emission very far away from the gases. So we don't think that that's the explanation. And we are left with accretion disks about intermediate mass as an explanation. And I will try to explain why this can satisfy all the observational constraints. First, if we know observationally that you have an X-ray binary, one of the components a black hole, so you have the accretion disk around the black hole that is accreted. Often during quiescence, you get H alpha profiles with 2 peaks, which is very close. Very little continuum and very, very high. This is observed in local stellar mass black holes, so they are able to produce the redshifts, so you have an accretion disk. Now, why they have to be intermediate mass black hole? This is a very naive, bold explanation, but just to have an idea of how this should be good enough. Simply, if you scale the fluxes of these stellar mass black hole, fluxes that are observed, and try to match with the fluxes that we estimate of these schemes, there's a factor of the order of 10 to the 3 to the 6 in flux. And if you maybe scale the flux with the mass of the central black hole, then you end up with a super intermediate mass. So black holes in the range of 10 to the 3 to 6 or so. Okay. How can you get H alpha that is much larger than H beta? So one of the possibilities that you have dust. I'm not going to discuss that thing, but I'm going to focus on this SED of an accretion this around a high redshift. This is a simulation, right? And this is an accretion this around supermassive black hole accreting very high rates, high redshift at the same time. But if you, this is a logarithm scale, so the prediction is that H alpha is at least 1 of the multipolarity of beta. And the reason is that, we typically, at least those that are trained in H2B interpretation, are used to the production of these H alpha and H beta combinations. You have proton, electron, that recombine and they produce all the lines of H. And then this fits the ratio between H alpha and H beta that you would expect. When you, for that thing to depend on dominant mechanism to produce H alpha and H beta, the densities have to be very low, but these are the typical densities that we need to reach now. When you have an accretion disk, the densities are relatively high compared with the densities that you have in the accretion disk. And so the excitation and the production of H alpha photons is different. You have collisions, and those are the collisions that excite the different levels that scale down and produce the light. And so it is The mechanism of excitation is very different from the simulation, and this is what produces in this simulation what produces the difference in the extra dimension. Okay. Yeah, we think that accretion is around the minimum of all the observation constants. And so let me quote here Sherlock Holmes that says that when you have eliminated the impossible, whatever remains, or either improbable, must be the truth. And I think this is actually what we are trying to show here. So that even if it's personally crazy, there's no other explanation for this. Some of you who have been. And so we stick with that idea of these signals being produced by the minimum stuff in the halo of the galaxy, which is producing speed. Now, are these intermediate mass black holes expected? So they are very exotic. Some people, quite some people searching for them. So far, we haven't been very few. So we point out that now. But are they to be expected? And the answer is yes, of course, really. These are two reviews that you might want to check, two recent ones, about all the channels that are able to produce this intermediate mass black holes. But let me mention just a few very briefly. Primordial black holes. These are black holes that are produced when again, people have, they were proposed, they were rethinking recently to try to explain all the dark matter in the universe. So all the dark matter is black holes, of different masses, with spectrum of mass. Now, there are mechanisms to produce enough number of black holes to really account for the dark matter of the universe. Now, the problem is that observational universe, so when we discover a large fraction of dark matter is actually black holes. And this is a recent account of this observational constraints that we have. So this is the fraction of dark matter in the universe that could be accounted for by primordial black holes versus the mass of the black holes. So this is solar mass, this is kind of planet mass, and this is kind of dwarf galaxy mass. Okay, and the white area is the one that is allowed by observation. And of course, like typical stellar masses, you can discard that only a very, very small fraction, 2%, can be produced by primordial. But keep in mind that the amount of dark matter that we have is huge. Okay? So if you want to account for all the dark matter in the universe with black holes that are stellar mass, you need of the order of 100 black holes per star in a galaxy. Okay. So even if you drop the number of primordial black holes consistent with observation by a factor of 2 or 3, still plenty of black holes. So of the order of 1 per star in a galaxy. So tons of it. Another way, another reason why we think there should be plenty of the mass black hole is the fact that you need seeds to very early on in the universe. Seeds from where the supermassive black hole are sort of squeezed, which is 8 or so, are grown. So you need seeds that by accretion of gas or other black holes, they grow in the supermassive very early. Now, the process of a black hole merger is very inefficient. So you have to produce tons of intermediate mass black holes at the high ratio that merge together to produce a few supermassive black holes. But since the process is inefficient, you expect that many of these seeds still remain around. These are intermediate mass. So this is another channel to expect them to be patterns. And there is another thing, and this last one that I want to describe here, that comes right from the other in the mass spectrum. And it's the sources of gravitational waves. So we know that that there are black hole mergers able to produce observed gravitational waves. That the more massive ones are 2 black holes of masses of 60, 80 solar masses producing, well, a black hole of the order of 100 solar masses. Now, the progenitors of this merger cannot be produced by itself. That's what the standard stellar evolution is. So these black holes have been growing by mergers of smaller black holes over time. Now, are there bigger black holes, or is this all what we get now? So far, we are fully constrained by the sensitivity to gravitational waves that we have nowadays. So we are not, if there were black holes more massive than we're imagining, we will not be able to detect them. And this is what is supposed to be explained here. So this is the sensitivity, and this is the frequency of that you have to detect to measure the mass of the black hole, right? So this is LIGO sensitivity. So this is the reading we have access to. And so there's a kind of wall here where you cannot easily go into, and you have to go to space. So now, if you pay attention, these curves here are the range of frequencies that you expect from the merger of 260 solar masses per hole, like in this case, and right at the limit of sensitivity of light. Now, if you start merging black holes that are more massive, then the frequencies are much lower, and you don't have access to those black holes. So really, we feel that there are plenty of more massive black holes will be detected in the future, but they are going away. Now, despite the fact that you expect black holes for many different arguments, we have detected intermediate mass black hole. We have detected and confirmed very few so far. And so this is all what I wanted to say, and I'm going to finish with the summary. I'll go quickly through the summary. So first, we tried to detect cosmological gas that was feeding star formation in the galaxy through its emission in H alpha. And so we detect, really, we select a number of galaxies in the MUSE-Wide field where H alpha was accessible. And in these galaxies, we detected of the order of 120 H alpha emitting clumps. The surface brightness is very low, it was 17.3 in the log in CDS units. We don't think that these signals are created either by instrumental artifacts that decline residual or high resolution interlopers, so they are astronomical. Often they have two peaks. The H alpha line is split. By the way, I haven't mentioned this thing explicitly, but it's clear. It's very hard to get H alpha from two peaks. So this is an illusion. So H alpha shows we see a bit most of the time. So the main scenarios or cases where you get this double peak, but the standard thing is to have H alpha with a single peak. Okay, and in this case, most of the profile they do have two peaks with a separation of the order of 150 kilometers per second. The clumps are spatially unresolved. The signals are not uniformly distributed. They know the existence of a central galaxy, for instance, the distributions of azimuths. And so, if you put together all these constraints, you can describe really most of the scenarios you can think of, and we are left with the possibility that this emission is produced by accretion, little accretion rates around the mean mass of wandering the halo of the galaxy. And that was it. So I don't know how on time or not.
We can have some questions.
Yeah. So I will put the questions if you have any. People have been patient enough to listen.
Sorry.
I
would need the microphone. If there are questions in the room, then... but you will have to answer them.
Jorge, you are observing H alpha. Is there any other kind of signal that would allow you to confirm your hypothesis, for example, with the James Webb telescope, because they are observing a time in the universe in which the presence of these objects will be much higher than today?
Yeah. So the question was.
If there is any other signal?
No, I understand. So I'm just repeating the question just in case it wasn't clear for those that are attending through Zoom. So the question was whether, I mean, what are the observations that can confirm or discard this fact? And there are plenty of different ways. So if they are accretion disk around black holes, we expect them to emit in X-rays. So if you go deeper in X-ray, you expect them to show up. If they are dusty, and even if you don't see directly the continuum that is produced by the disk, and this is one of the reasons why the theoretical SEDs are not blue, you expect them to emit in the infrared. And so this is a place where James Webb comes into play. So yes, James Webb is going to be particularly useful. And even more, this is a cosmological field. So the reason why people studied this MUSE-Wide was not to study local galaxies. They are just the contaminants of the background sources. So this is one of the typical fields that is going to be targeted by James Webb. So very soon we will have James Webb, and we expect these features to emit in continuum in the infrared. Now, another way is that, of course, we don't detect H alpha or the oxygen-free lines, and we don't detect a continuum. But this should be a problem of sensitivity. So if you go deep enough, then you have to detect H beta, you have to detect the continuum, all this stuff have to be there. Now, the problem is that these are 1 hour integration with MUSE, and it's very hard to beat. So if you want to increase the signal to noise by factor 3 or 4, you end up with, I mean, these are 40-something fields, 1 hour integration week. So you're talking about things that are hundreds of hours with MUSE, and this is really impossible to make. Fortunately, the central field, I mean, these are kind of auxiliary fields for the central field with the good south field. And this is going to be released. And these are like 180 hours on a small field with MUSE. So we expect to see all the features if we manage to detect a few of these black holes in this very deep field. So just to sum up, yes, there are many things that can be done to confirm or discard this thing, and we are thinking in how to do that, and we are working on that, by the way.
More questions? No. Are there questions in the Zoom session? If not, then we can go for.
There is another question.
Okay. There's one question in the Zoom. Should I read it to you? It's in the chat.
Jorge, I was just meaning to ask. Sorry, can you hear me?
Yeah, I do.
I was just asking, wondering. First of all, have you computed the X-ray flux that these sources would emit in the accretion disks, and whether this would be detectable with, say, eROSITA or any XMM or any X-ray satellite?
Yeah, we did that estimate, and they are right below the detection threshold that we have now. I'm not an expert in any rays, but it's the deepest thing we can have nowadays. So this 7 million second.
But that's XMM, I guess, right? That's the so now with eROSITA data, maybe you can actually, and eROSITA data is about becoming public. So
but yes, we did that estimate.
Okay. So for eROSITA, all right, yeah. Okay. And then would you expect to see any of these? I mean, this is at redshift 0.35. You have just 100 sources. I forgot the area, but it was a relatively small area, right? Like, what are the chances of finding this? You know, if you work out the statistics of the abundance of these objects, wouldn't you expect to see this type of black hole mergers or black hole accretion disks in a more nearby universe, like in the local group or in Virgo or in, you know?
We don't see mergers. Okay, we just see faint H alpha emission.
Sure. Mm-hmm.
And yes, I mean, the idea that we have is that there are many black holes that are naked. So most of them we are not detecting. And only those that just by chance are accreting now at a significant rate, they are producing this emission. So there should be tons of them around. And for reasons that we don't understand, we don't know how these black holes get their accretion this around. There may be a pristine gas that was there from the formation of the black hole that is for some reason unstable now and is get accreted, or they just happen to find a
gas cloud in the circumgalactic medium, and this is used, or they are like a tidal disruption event. They are eating now stars that happen to be nearby, or who knows. So yes, they are going to be everywhere, really. That's the idea that we have.
Yeah. Nice, thank you, Jorge. I'm sorry for the mess.
Okay.
Okay, one last question in the room. I think there was.
Just a simple question, Jorge. You say that each beta can be surprised because collision of the excitation, right? What are the...
I think I don't think that is collisional rate, the excitation. It's the excitation that is through collision. So it's hydrogen, neutral hydrogen excited by collisions. That's my understanding.
So H alpha is not very nice, but
no, it's not recombination. It's collisions from. I mean, you have neutral hydrogen atoms that collide with electrons, and this gives you the population of the different levels that cascade down and emit. I can give you the reference if you are really interested, but I think that's the issue. So it's not that collisions de-excite, it's that collisions excite because the densities are high enough.
okay, I'm confused.
Yeah, I can give you the reference of the paper if you are really interested.
Thank you.
Okay, thank you again, Jorge, and sorry for the delay and the inconvenience. I think we can go for coffee in the cafeteria and